Okay, so I think probability is something that you understand pretty intuitively. You've always known that the if you flip a fair coin, the probability of getting ahead is one half or zero point 0.5. And the reason for that is that uh, following this formula, you have a total number of elementary outcomes of flipping a fair coin. You could have heads or you could have tails. And the number of elementary outcomes in your event, which is heads, is 1, so 1 divided by 2 is 1 half. And this principle can get you quite a lot. For instance, suppose you're sitting in front of a group of 10 people, 3 of whom are men. So if you select a person at random from that group of people, the probability that the person you select will be a man is 3 divided by 10, or 0.3. Okay? And there's a couple more examples of that here. We also use the term probability to describe empirical situations, and here's a couple examples of the use of the term probability to describe empirical things. We also use the term probability to describe your subjective estimation of something. And I've got a couple examples here. I believe the probability of having a class canceled, well, next winter because of snow is about 0.5. That is, of all the years that I've experienced teaching, about half of the time I'm going to have at least one snow cancellation. Okay? So now we turn to something more theoretical. Random variables. What is a random variables? In the case of a random variable, you've got an experiment with numerical outcomes, and the numerical outcomes are called random variables. And you classify random variables as either discrete or continuous, and there are very different ways of handling these two types of random variables. A discrete random variable takes on only specific values. And the example I give here is flipping a fair coin 3 times and recording the number of heads I get. That's your numerical outcome. So I have a random variable with 4 possible values: 0, 1, 2, and 3. Those are the only things that can happen. I can't get 1.5 successes. A continuous random variable can take on any numerical value within some interval of numbers. For instance, I weigh myself every morning, and there's a range of about 5 pounds where I can get a value. Now, my scale only goes up to, well, it only measures to an accuracy of 0.1 pounds. So those are the only values I can possibly get. And conceptually, though, I can vary by much smaller amounts. It's just that my measuring device can't accept it. So I consider the weight that I take every morning of myself to be a continuous random variable. Okay, every random variable has 4 standard functions: the p function, the q function, the d function, and the r function. And for a normal random variable, xxxx is replaced with norm, and for a binomial random variable, xxxx is replaced with binom. And you can look here. This is a, a good explanation of all of the different types of functions that you have associated with every random variable. So let's look at a very specific type of binomial random variable. Here are the requirements. A simple trial repeated n times and has only 2 possible outcomes. One of the outcomes is defined arbitrarily as a success. Success doesn't mean good. It simply means that this is what you're counting. And the probability of success is a constant denoted p. The trials are independent, and the success or failure on one trial does not affect the probability of success on other trials. So here we have a famous formula. The binomial probability distribution gives us the probability of exactly x successes given the values of n and p, and this is an example of a D function. So if you have, if you're looking for the probability of x successes out of n trials with probability p of success on one trial, then this will give you the probability that you're looking for. When I was learning statistics many years ago, we actually did have to go through these computations. We did not have computers in those days. Now, you have the D binom function, and this is the probability of getting 5 trials out of 10 successes with a probability of success on one trial of 0.2. So a lot of people think that learning the binomial distribution meant that what you understood was how to go through the process of calculating this thing. Well, that's silly in 2023. We simply use the formula. It's kind of like trying to do a square root. Doing this computation is like trying to do a square root by hand. There is a way to do it, but nobody knows how to do it anymore since every simple calculator has a square root key. The human work that you have to focus on is how to look at a situation and decide whether or not the binomial distribution is appropriate for that situation. That is the human's task. Then the second thing, which is much easier, the second part of the human's task is much easier, is how do you ask the computer to do its part? And I've got here 1, 2, 3, 4 examples, and you should stop right now and think through these 4 examples and decide whether or not the binomial distribution is appropriate. And after you've done that thinking, click here for my explanation. That's a YouTube video in which I explain these 4. Okay? And I've also created some exercises on the binomial distribution for you to play with to get familiar with it. Okay, now we come to continuous random variables. And the most famous continuous random variable is the normal distribution. And for a normal distribution, to calculate a probability, you have to be talking about the probability that the number falls within an interval. The probability that the number takes on a specific value, like a point value, like 0.1 or 0.3 or 0.4, is 0, because you have to have an area, and a line segment has no area. And I've got here a function which I've written up to, which will actually show you what you're doing when you calculate a normal probability. And there are 1, 2, 3, 4, 5 things that you can specify. You can specify a lower bound to your interval, an upper bound to your interval. You can specify the mean of the normal probability distribution, and by default we accept 0, but you can override the 0. And by default the standard deviation is 1, although you can, you certainly would in almost every circumstance change the standard deviation to whatever you've got. And then there's a label. You can describe that. And here's the code, and if you want to play with this thing, you have to copy the whole thing starting from here at mynormprob and ending down here. The very last line in this block is a test run with an upper bound of 1.5. So you're looking for the probability that your normal random variable, which is here because of the defaults, a mean 0, standard deviation 1, normal random variable. And this is what the program, a little snippet of code produces for you. This would be the 0.1, 0.5, and you've got the area all the way back to the left. Okay? And you can change all of these parameters. Basically, you could get the same number just by running the simple pnorm function, pnorm 1.5, and that gives you about 93%. And if you want the area to the right instead of to the left, you take 1 minus pnorm of 1.5, because the entire area from negative infinity to positive infinity is going to be 1. Okay? And here's a couple more examples of the function. And here's a good example of finding the area between 0.8 and 2.4. So here's the 0.8, here's the 2.4, and the area between those two, that is between a lower bound of 0.8 and an upper bound of 2.4, we have 0.204. Now, it would be extremely unusual in the real world to be dealing with a standard normal distribution. Normally, you're dealing with a distribution which has a very different mean from 0 and a very different standard deviation from 1. In the old days, what we did, we only had the one standard distribution table, and we had to calculate a z-score by subtracting the mean from the value of x and then dividing by sigma. So here's an example. If I have a mean of 100 and a standard deviation of 10, and I have an x value of 115, when you do a z-score, you get 1.5. And what we would do is go back and calculate the p-norm of 1.5. Actually, in the modern era with computers, we take the p-norm of 115 and just specify that the mean is 100 and the standard deviation is 10. Going backwards, sometimes you're in the opposite situation. That is, you know that the probability to the left of you is 0.9, and you ask, well, what is the z-score if I have a p-norm of if I have an area to the left of 0.9, where am I? And the answer is you are with the standard normal, at a value of 1.28. And you can see that the p-norm and q-norm exactly cancel each other out, or you have the exact opposite. P-norm and q-norm are exact opposites. And I have created a series of exercises on the normal distribution and put them in the module in Canvas, and you can get to them right here. Okay? And that's all.